I'll talk briefly about differential. Okay, and I said df is fx dx plus fy dy, which is exactly what you just asked me about, except I've got notation around it, okay? Because I asked you to actually calculate the differential, because the differential is basically your tangent plane approximation. And you calculated a percent difference between the tangent plane approximation and the actual value of the function, right? So you know what I'm talking about here. Now let's back up a second. If you got a function of one variable, then your differential is this, okay? And I said delta x. It's actually, we write this as dx. It's just another way of writing df dx equals f prime. I mean, it's not an algebraic rearrangement, but you can prove that this and this are equivalent, because the simple reason is that f prime, where prime is the derivative of f with respect to x, is the rate at which f changes with respect to x, right? If you multiply the rate at which f changes with respect to x by the change in x, what do you get? The change in f, right? Now, actually, you don't get it, because this is evaluated at some point, and dx moves you away from that point.
So you're going to get it if dx is...
So you're getting an approximation. You're getting the approximation that would result if the derivative didn't change over this interval.
So if you take the limit as dx approaches 0, you get the actual?
Well, yeah, and the closer, the smaller dx is, the closer this approximation will be to the actual change. And the picture of that, you should remember from first semester calculus, you got this. Okay? There's your function. Here's a point on the graph, and here is your tangent line. Its slope is f prime, right? Derivative of f with respect to x. Well, if it's a smooth curve, then the tendency is, and of course you can make up smooth curves that don't exactly follow this, but the tendency, if your second derivative doesn't change, if second derivative doesn't change sign, so your concavity remains the same, and that will be the case in some neighborhood of the point. If you're close enough, it's going to be true. If you go too far, well, the curve might go like this and it won't work anymore. What I'm about to say is not going to be true anymore, but the further you get from the point, the worse the approximation is. So if you have a delta x like this, say a dx, and this is a little bit of an abusive notation, I've never been able to figure out a way to get away from it. So you have here an error, right? And we would call this our delta x. And I've got the arrow going both ways, and I shouldn't. So this thing here is like your delta f. The difference between the value of the function and the value of the approximation, okay? And I'm not going to worry about which way that arrow goes, just to give you the idea. We'll straighten the rest of it, okay? So this is just to put you back in the context of what you should know from first semester, but nobody ever does, okay? I don't know what people learn in first semester. It's how to follow a few rules without knowing what any of it means. But review this and then put it in this context where it's not hard to understand, because you understand tangent planes and you understand how the tangent plane is, it's a plane, and if your function, as most functions do, has some curvature in the vicinity of a point, then it's going to curve away from the tangent plane, right? And this is the approximation given by the tangent plane. Delta f is like f at the x plus delta x, y plus delta y point minus f of x, y. Okay? This is the difference or actually I shouldn't say the difference, I should say the change in the actual value of the function. So it's a change in f. That's, I'm going to say between, but I'll say from x, y to the point x plus dx, y plus dy. Okay? Now when I write a dx or a dy in this context, these are not infinitesimal quantities. Okay?
They're more like delta.
They're more like delta x's, but we don't want to use the delta because we're using it here and the notation is a little bit ambiguous. Okay? Kind of like it is here. Hopefully that ambiguity, bothered you when you did first semester calculus. Probably not. Okay. There's an ambiguity in the notation. So we just accept the notation as it is. Okay, so we have this, right? So df differs from delta f. Delta f is the exact change. df is tangent plane approximation of the change. For small, dx and dy let's write df first. df is close to delta f. Okay? Now we can quantify that, we can prove that. But intuitively, that's what it is. And why is it that? Well, in terms of our picture, our standard picture, here you got the point x, y, right? Here. And you got a point out here. You got some delta x. Sorry, we're not going to call it delta x now. I keep wanting to do that, but that's like a dx and this is like a dy, right? So here's your point x plus dx, y plus dy. So the value of the function at this point might be up here somewhere. Okay? The value at xy, of course, we'll say is this. Okay? Now how do you get from this value to this value? Well, if you go along here, you'll have some slope, right? And you have a rise here. Okay? And the rise is fx dx. Make sense? I mean, fx is the rate at which the value of the function changes when you move in the x direction. Well, if you move that far in the x direction and the rate is fx, then the rise, the difference in the value of the function from here to here is going to be fx dx. And then you're going to have a rise from here to here. Fy dy. Okay? Now, from here to here, you're going to have a rise. Okay? So from here to here, your rise, it is not necessarily the same as Fy dy. Because you've moved to a different point here, and the derivative at this point is going to be different, right?
But it's going to be very close.
Huh?
But it's going to be very close.
Yeah, if you got a small interval and the function is smooth, you know, differentiable, bounded derivatives and stuff that we talk about when we prove this, okay? But for most functions you'd be dealing with as an engineer, that's going to be the case, okay? So you have some rise, okay? Now, I drew the rise up to what I said was the value of the function. I'm going to say the function actually goes up a little higher. Okay?
Why?
Well, because the rise here is not exactly the same as the rise here. Well, actually, I mean, these are approximations, okay? You know, that was a bad answer. These are approximations. The function might actually be curving concave up or concave down at this point, right? These are linear approximations, okay? And that's an important word. Linear approximation, it's on a plane. A plane is flat, has no curvature, it's linear. Just like a tangent line is linear, okay? The plane just kind of generalizes that linearity. Okay, this is getting a little long. So I'm going to cut the video and just continue.